two events occur at the same place in space. So for example, suppose there's this person here riding in this train. And let's forget about the outside of the train, and let's suppose we are inside the train with this person. And I take out my laser pointer, which I left in my office, I guess. I don't think I have it. And I take out the laser pointer and I stand in front of this lady here, and I just shoot a beam towards a mirror a distance d away from my laser pointer. So I just stand over here, right? Oh, hi, what's up? You know, you enjoying the train ride? Yeah, okay, whatever. Then take out my laser pointer and I just boom, boom. I just shoot a beam of light towards the mirror, and then it comes back. So it goes boom, boom. Yes. So the distance from the aperture of the laser pointer to the mirror, let's call it d. That's what it's called. Right. So that's the source of the light. It goes boom, mirror comes back. Right. Let's say that the time that it takes this light to go from here to the mirror and come back is delta. We can either define it going towards it or coming back. Let's say delta t0. Or actually, we're going to be thinking of that frame of reference as moving relative to the ground outside. So this is S prime, you know, the moving frame at constant speed u along the x-axis. And then there's going to be someone from which we're going to be looking at this also from the outside. That's another frame of reference on the ground outside, right? So the light starts over here, goes this way, hits the mirror, right? If you're inside the train. Right? So in the frame of reference of the train. And it goes that way, and then it hits this thing, right? A distance d away, and then it comes back to the same spot. So the two events are the emission of the laser light and the receiving of the laser light back over here. Those two events occur at the same space, at the same point in space, right? I shoot it, goes boom, boom, goes right back. So therefore, the time that it takes the light to go here and back is delta t sub 0. That's the proper time. Right? Inside the train, which is in the S prime frame, or the S prime frame. I think that's the notation that's used over here. The light travels at speed c. So what is the relationship between this distance between the laser pointer and the mirror on the wall of the train, and the speed of light in this medium, and how long it took the light to make the trip, right? So at t is equal to 0, it leaves and then it comes back, right? So what is the relationship between them? Well, what is the total distance that the light travels? D plus D. So the light travels a distance of 2d, and that distance has to be equal to the speed multiplied by the time. And the speed of the light is c, and the time that it took it to make that trip is delta t sub 0. And because this is in the moving frame, you could say this is, you know, delta t prime, or maybe I'll just delta t prime because it is in the moving frame. It's just that this is the notation that's normally used, right? So we get that this d is equal to c delta t naught, the proper time, divided by 2. Now, what would this same two events look like according to someone who watches these two events taking place from outside the train, on the ground? Well, to this person, when whoever was standing over here next to this lady, whenever that person pressed the button to, you know, emit the laser light, that person was there when the light left the laser pointer. And then the light traveled to the mirror, and as the light traveled to the mirror, the train was moving to the right. And then the light hits the mirror, so to this person, right, as the light travels towards the mirror over here, right, the mirror is going this way, the laser pointer is moving, so the light in this guy's space goes this way and hits the mirror. And then, you know, the light reflects, right, and so when the person over here receives the light back, that person is going to be over here. So these two events, the emission of the light and the receiving of the light, do not happen at the same point in space. He says, no, when he fired the laser pointer, he was there, but then when he got it back, he was there. Those are two different points in space. So that's not the proper time. In his frame of reference, this is X, Y, Z, so this is just delta T. So what does this person see? So let's say this is outside the train. Right? So this is the S frame. I wrote plane over here. So good. Right. All right. So then what that other person sees is the light starts over here, it goes this way, hits the mirror, and then goes this way, right? And then it's received over there, right? So the light travels at speed c, right? This distance over here is d. The motion is along the x-axis, the common x prime axis, not along the y-axis, so this distance remains the same along the y-axis, right? Now, in this person's frame of reference, t is equal to 0 over here, and the light comes back at a time delta t. Right, so in this frame of reference, it was emitted at t is equal to 0, the light came back at delta t sub 0. Right, so this is the emission of the light, and this is, reception of the light, or getting the light coming back. Now, to this person, the whole train with the laser pointer, the mirror, and everyone is moving at a constant speed, u to the right. And from symmetry, what will be to this person outside, right? This person measures delta t. That's the S frame without the prime. For the whole process, right? Delta t. So how long does it take the light to go from here to here? One half delta t, right? And during that time, this train is moving at speed u to the right. So what will this distance be?
U delta t over 2.
Right? It's the speed u multiplied by the time that it took it to go from here to there. So it's gotta be, u times 1/2 of delta t. This is speed multiplied by time is the distance. Right? Correct? And what is this distance over here along this, speed is c, what is this distance over here? No, but instead of this one here, it would be, the time to go from here to here is 1/2 of delta t, traveling at speed c, different from traveling at speed u. So what is this distance over here in terms of c and delta and that? C delta t over 2. Right? So this distance has to be the speed at which the light travels here, which is speed of light is c, divided by how long it took it to go from here to there, which is half of the whole delta t. But the train, so the light goes this way, in other words, that's the light traveling at speed c, but the train is not moving at the speed of light. The train is moving at speed, at speed u. So it's the speed of the train multiplied by that. Now, if I use Pythagoras theorem here, what do I have? I have that u times 1/2 of delta t, all of it squared, right? Plus d squared has to be c squared delta t over 2 squared, correct? That's Pythagoras theorem. And this, this squared has to be this squared plus this squared. Now, I have an expression for d. So now I can take this d, and I can plug it in here, and I can express that distance d in terms of the time that's passing by, that's inside the train, by someone inside the train. So then this becomes u squared, well, over 4, right? Delta t squared plus, and instead of d squared, I'm going to write c squared delta t naught squared over 4. Equals c squared delta t squared over 4. And clearly we can cancel the 4's, right? And let me bring this term over to this side. So I'm going to get c squared delta t naught squared equals c squared delta t squared minus u squared, the same delta t squared. So I can factor out the delta t squared. So this is c squared minus u squared times delta t squared. I mean, all I'm doing is middle school math, right? I mean, it's just Pythagoras theorem, squaring this, moving one thing to, this is just really elementary algebra here, right? So I have that. And what if I factor out c squared from here? Then I get 1 minus u squared over c squared times delta t squared. And then this can cancel that. And now what if I take square roots on both sides? Then I get this equals square root of 1 minus u squared over c squared delta t, right? And so the time interval as measured by the person outside the train is this divided by the square root of 1 minus u squared over c squared. And that's the time dilation formula that I also arrived at yesterday using one of the, another argument using what's called the Lorentz transformation equation. So that formula is the one that we talked about. And, because 1 over the square root of 1 minus c squared over c squared is defined as gamma, you can write this as gamma delta t naught. Also. Same thing. So this is the time dilation. Okay. So I just wanted to show you another relatively simple way of obtaining the time dilation expression, which is the one on the board, right? So let me move ahead to, that's another argument there. So I wrote this Lorentz transformation equations on the board, right? That relate the space-time coordinates of an event in the moving frame S prime to the space-time coordinates of the same event as measured by someone in a different frame of reference, S. So by space-time coordinates, I mean x, y, z, t, or x prime, y prime, z prime, t prime, right? It's just the coordinates of the location, but also the coordinates of time in that particular frame of reference. So, these are the Lorentz transformation equations. I think there's a homework problem. I mean, I haven't looked at it in a while, but I think in one of those, that very long set of problems, that I recommend you do for homework, there is a problem where you end up sort of deriving this or using this to some extent. But we got the Lorentz the Einstein velocity transformation equations. So I want to write down Newton's second law of motion. You think of Newton's second law of motion as F equals ma, right? And you think of linear momentum as mass times velocity, right? mv is what you learned in physics 185. But the expression for linear momentum becomes something different, right? It becomes something like given by this expression. And then there is an, F equals ma, when an object is moving very fast, close to the speed of light, and you push in the same direction that the object is moving, the relationship between the force and the acceleration is given by this expression instead. Just it's given by this. So I'm not deriving this, I'm just telling you that's the result. This is how F equals ma should be thought of for all velocities. Now, notice that if the velocity of the object is very small compared to the velocity of light, or the speed of light, v over c is very small, and if you square that, it's even smaller. So then this is 0. So 1 minus 0 is 1, and 1 raised to the 3/2 power is just 1, and you just recover F equals ma, which is what Newton wrote down. So what Einstein did was, he didn't say, Newton, you're wrong. He just said, your expression, F equals ma, is only good if the velocity of the object is small compared to if the speed of the object is small compared to the speed of light. But if it's comparable to the speed of light, we have to fix it. It becomes something different. And so it becomes this. But notice again that if you take the limit as the speed of the object is very small compared to the speed of light, material objects that move around space, then this is like negligible. So you get 1 minus 0. So you get 1 in the entire denominator. I mean, gamma goes to 1. And so F equals ma, you recover Newton's expression. Right? But let me say something about that formula, because you have heard, I'm sure, at some point, that the speed limit of any material object in the universe is the speed of light in vacuum, right? And like nothing moves faster than light. But that statement should explicitly say that nothing with mass moves faster than light. In fact, it doesn't even move at the speed of light. It can move close to it, but not at the speed of light. You would need an infinite amount of energy to speed something up to the speed of light. So you can approach it, but not make it go at exactly the speed of light if it has mass. So, but let me just say something about that comment, the maximum speed limit of anything meaning, anything with mass, right, is the speed of light in vacuum. So that comes from Newton's second law not Newton's, should we say Einstein's second law of motion? Yeah, it's in Newton, right? How about we say whatever you want to call it, okay? F equals ma, but then you have this factor over here, 1 minus u squared, or let's say v is the speed of the object. I guess I called it v over there, c squared, and then to the 3/2, not to the 1/2. Usually you'd see a lot of square roots of 1 minus v squared with c squared in the denominator. So this is the speed of the object of mass m, right? Now, so Einstein wrote this, and the question is this: what is a? According to this, right? So the acceleration would be f divided by m multiplied by 1 minus v squared over c squared to the 3/2. Right? If I just rearrange and I solve for a. Because, I remember a professor of philosophy here at OCC once came to me and he said, what's up with nothing being able to speed up to the speed of light or faster than light? And what he was arguing was that, if this is the mass of an object and I push it, right? And I just keep pushing it, maybe a small force, right? But I push, it'll speed up, it'll get an acceleration this way, right? And so this force, even if I push with, let's say, 10 newtons, right? Then it'll speed up. And if I just give myself an infinite amount of time, then at some point this object, it might start from rest. And then later on, much later, it will be traveling at the speed of light. And if I keep pushing, it should be traveling faster than light, even later. So it should be traveling at a speed greater than the speed of light, if you keep pushing. So he says it's just a matter of time. But he was thinking of F equals ma, right? For the same mass, if you give it the same force all the time, you're going to get the same acceleration. Eventually, you're going to make it reach the speed of light and then surpass the speed of light. Thing is that as soon as this object begins to move very fast and close to the speed of light, this is not good anymore. You have to go to this. And when you have to go to that, the acceleration of the object becomes this. And what happens if you say, okay, the thing has reached the speed of light? Well, what happens if v is equal to c? Then what becomes of the acceleration?
0.
It goes to 0. And if the acceleration is 0, it's not going to speed up anymore. So you can't really surpass the speed of light. So what happens is that constant forces gives you constant accelerations, right? If the speed of the object is small compared to the speed of light. But what happens is that for the same force, if you think of the force as being constant, right? The faster and faster, the closer the object moves in speed to the speed of light, this term over here grows and gets closer to 1, and then so this 1 minus that big number that's getting bigger, closer to 1, this whole term gets smaller, 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 so the acceleration is not constant. So a constant force doesn't necessarily give you a constant acceleration. We say that in Phys 185 because we're always considering objects that are moving relatively slowly. But so that we are in this realm over here, F equals ma, right? But if you push long enough so that at some point the object has a speed close to the speed of light, you can still push with a constant force, but the acceleration is not going to be constant anymore. The acceleration will get smaller, 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 and if you manage to speed up the object with mass, you gotta have a mass in there, to a value of the speed equal to the speed of light, then this v becomes c, and c over c is 1, and 1 minus 1 is 0, so then the acceleration is 0. And then, therefore, the object doesn't speed up anymore. So it will never be greater than the speed of light, because keep pushing, not a problem. It's not an issue of how long you can push, right? So that's one of the messages. I think one of the important messages over here is that constant forces do not cause constant accelerations anymore. Because in Physics 185, we teach the kinematic equations. V final equals V initial plus AT. Displacement equals V initial multiplied by time plus a half AT squared. V final square equals V initial squared plus 2A times the displacement, right? Oh, and how do you know the acceleration is constant? Well, if the forces are constant, the acceleration is going to be constant. That's the argument that we use. But only because we are in the limit of very, very small speeds. Constant forces do not lead to constant accelerations if the speeds involved get close to the speed of light. Okay, so that's one comment. Now, what is a formula that you learned for kinetic energy? Back in Physics 185. So, in Physics 185, so I'm sorry that you now have to unlearn things that you learned in Physics 185. That was just to get you ready for, the good stuff. If you want to think of it that way. It's like, I guess it's not fun crawling, it's more fun running, but before you run, you gotta learn how to crawl and walk. So in Physics 185, you learned that kinetic energy is defined as 1/2 mv squared, right? So where does that come from? So the work energy theorem says that the work energy theorem says that the sum of the work done by all the forces acting on something is equal to the change in kinetic energy. Now, so where does that come from, and what is kinetic energy, right? And this is, of course, we're talking about the translational motion of an object of mass m moving at speed v, right? So work, see, the sum of the work done by all forces, all of them, is the same as the work done by the net force. Because all the forces acting together will give you the net force, the resultant force, right? And when you're learning about vectors in chapter 1, in Phys 185, right? This is just the work done by the net force. I mean, if I push an object on that table, for example, here's the table, here's the object, I push this way, that's me pushing. There's a normal force like that, there may be kinetic friction like this, right? There's a force of gravity like that, right? So if I sum all the forces, that's just called the net force, or the resultant force. So the physics that I'll get from all of these forces acting on the object is identical to the physics that I get if I just replace all of these forces by just the net force. Maybe the net force is this way, maybe. But this represents the sum of all the forces. So the work done by this force, plus the work done by this force, plus the work done by that force, plus the work done by that force, is the sum of the work done by all of them. But that's equivalent to the work done by the force that's equal to the sum of the forces, right? And so I can write this as, and the definition for the work done by any force is that force, which I'll just call it the net force, right, with an infinitesimal displacement. Now, Newton said that this net force is what? It's ma, right? N times dr, right? And m is a constant in classical mechanics, so I can pull that out, not in relativity, because matter can get converted to energy, so then the mass doesn't have to stay constant. And then I have a dotted with the r. And so, but what is a? Isn't a, acceleration is the derivative of velocity with respect to time? I'm sorry, I'm going kind of, I don't know if you like that. Maybe you don't like that, so I'll just maybe do it like this. So you see the various steps. And then I'll take the m out, and this is a dot dr. Now, that way I can use this. So all of this is just the sum of the work done by all the forces, right? Now, so the sum of the work done by all the forces is equal to m, and then the acceleration is defined as the derivative of the velocity with respect to time, and then that's dr. Now, what is this? What's dr dt? The velocity, right? So this will be m, and then this will be v dotted with the v. And, well, what is the integral of v dv? V squared over 2. From, what if I accelerate this thing from rest? Or I don't have to accelerate it from rest. Maybe, and maybe I can accelerate it from v initial to v final. So this would be v final, and this would be v initial. So this becomes 1/2 m v final squared minus 1/2 m v initial squared, right? And that's the sum of the work done by all the forces And notice that the sum of the work done by all the forces is equal to something that just depends on the final speed and something that just depends on the initial speed. I don't care what the speeds are in between. By the way, when you write a vector squared, that means this vector dotted with the same vector, right? That's v squared. That's what that is. But how do you do a dot product of two vectors? It's the magnitude of one vector times the magnitude of the other vector times the cosine of the angle between these two vectors. But they are the same vector, so this is the cosine of 0. And the magnitude of that velocity vector is just written as v. The magnitude of that one is just written as v. The cosine of 0 is 1, so you just get v squared. So the vector notation disappears, right? So I can write this also as 1/2 m times the speed squared, final speed squared minus 1/2 m times the initial speed squared. That's how you saw it back in Phys 185. But since this is written as the change in kinetic energy, right? Then you can think of it as kinetic energy final minus kinetic energy initial, right? And if you compare that, and if you set it equal to this, well, then this has to be this, and this has to be that. So here you define kinetic energy as 1/2 mv squared. That's how the 1/2 mv squared, that's where the 1/2 mv squared comes from. It comes from writing the work energy theorem, right? And you realize that once you do this, once you just work on the left-hand side of this equation, in the end, all that matters is the mass of the thing, which stays the same, and the speeds, the initial speed and the final speed. And then you just say, well, this is energy associated with the speed of the thing, with kinetic energy, the energy associated with its motion. So it's defined as kinetic energy, and it is then defined as, 1/2 mv squared. That's the kinetic energy that you use in Phys 185. And in Physics 280, when you consider the motion of charged particles in an electric field, in a magnetic field, that's the expression that you use. Now, but this definition of kinetic energy as 1/2 mv squared depends on us having written Newton's second law as F equals ma. Correct? What if I do this problem all over again? But now instead of writing F equals ma, I write it like this. So what will be the new expression for kinetic energy when I get to it at the end? And I could have done this also by saying, suppose you increase something from some initial speed to some final speed, and let's say the initial speed is 0. I could have just said, suppose the initial speed is 0, then this is 0, then this is 0, then this is 0, then this is 0. And at the end, because it's not moving, because initially it wasn't moving, then you just have this is 0. So then kinetic energy is just 1/2 mv squared. That's another way of doing it. So what I like to do is, I would like to do this again, but instead of using Newton's second law of motion written as F equals ma, I'm going to write it as F equals ma divided by 1 minus v squared by c squared raised to the 3/2 power. What if I do that now? So let's see what we get. Can I erase this now? So in Physics 285, what is the expression that we use? So now this is number 2. So you'll see that the expression that we use for kinetic energy